Hello everybody, this is Dr. Hassan in Introduction to Digital System. Today's topic is the counters. And the overview of this topic is, at the beginning you need to know that counters are important components in a computer because it's counting either increment or decrement. As example, 0, 1, 2, 3, let's talk about decimal here. 0, 1, 2, 3, 4, 5, or into 10 as example. Or 10, 9, 8, 7, this is decrement. So counting is important, and there are many applications for counting. Example of them, just simple example, is the clock. Okay, we need it in a computer and many applications. There are two main type of counters. We have synchronous and asynchronous. Asynchronous, the only one letter difference between them, A, but the operation is different, the design is different. The asynchronous call also ripple counter, while synchronous counter is the other one. And from the name, when we say synchronous, they work together. When we say asynchronous or ripple, they don't work together. Okay, ripple counter, flip-flop output serve as a source for triggering the other flip-flops. Look, have a look. In a simple words, when we come to the synchronous counter, the flip-flops in this counter will work together at the same time simultaneously based on the clock coming for all of these flip-flops. While ripple counter or asynchronous counter, no, the output of the first flip-flop became input to the second flip-flop, and the second flip-flop output become input to the third flip-flop, and so on. So it is not working together. There is delay all the time. And we need to consider that synchronous counters are the more widely used in industry and in application. So it is the main type of counter available today in our technology. Now, counter is a register that goes through a prescribed series of states. Binary counter will count that will follow the binary sequence. It means 0, 0, 0, 0 when I talk about 4 digits, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, and so on. Got it? And if we have m-bit binary counter counts in binary form, we expected that we have 2 to n to 2 to power n minus 1 state. We mentioned that ripple counter triggered by initial count signal. Okay, so the output will go as input to the next flip-flop and so on. Example or application for these counters: watches, clocks, alarms, web browser refresh. Let me start with ripple counter. I will start explaining based on using T flip-flop, and then I will move to D flip-flop. For T flip-flop, you can see here, okay, definitely we have reset going to all of them to zero them. And if we look to the table here, from A0, which is least significant bit, to A3, which is most significant bit, we can see, let me start with A0. A0, the state change every pulse, 0, 1, 0, 1, you see, 0, 1, 0, 1, and so on, 0, 1, you got it? So always it's toggle, right? So what we will do is the logic will be 1 going here to as input to T, and the output coming from here, which is A0, least significant bit. Now if I come, I will change the color. If I come to A1, we can find that, okay, where at this A, okay, the toggle occurred. You can see at this A toggled occurred. The state changed from 0, 0 into 1, 1. Okay, and at this state another toggle occurred, 0, 0 into, on this state, as you can see here, 1, 1. So whenever a node change to toggled, then the A1 will toggle to. Okay, if we come, let me take another color. If we come to A2, when A1 and A node, both of them 1, 1, the toggle will occur. It was 0, 0 as you can see here, and it's changed to be 1, 1. What this tells me? This tells me the sequence of operation depend on each other. So if I come here, I can say that A node supposed to be the clocking the next flip-flop, while A1 clocking the next, which is A2. A2 clocked the next, as you can see here. You got it? So they in this way we can do counting. The same thing could be used for let me say using D flip-flop. Here also you can see this one coming here as a clock, and this is A1 coming here as a clock, okay, and this one coming here as a clock. We don't need here logic input. Directly we can take the previous state or Q dash A dash of the first flip-flop to be input to D, and then we continue. Okay, you can see here all of them you can see connected to the state input, so it can count, it can change. Now another synchronous ripple counter, you can see here I use we use T flip-flop, D flip-flop, let's use JK flip-flop. The same idea, the same principle. You can see here, let me take red color. This is the input for the next one, and this is the input for the next one. Output for the first one become input of the next flip-flop. Output of the second flip-flop become input for the next flip-flop, and so on. All of them connected in this way. And if we come to the operation, these are A, B, C, D, as you can see here. A, B, C, D of the first, second, third, fourth flip-flop. You can see this is A, this is B, this is C, and this is D, based on the clock. Okay, you see the clock, this is falling, right, not rising, flip-flop, sorry, falling. You can see here it was 0, it become 1, and so on. 0, 1, 0, 1, similar to the table in the previous slide, if you remember. Okay, now when we have 1 on A, which is enter as input to the next, then toggle will occur and we have 1 for next two steps. When 1 changed to 0, then it changed to 0. When 1 changed to 0, it changed again. You see toggle, whenever toggle we have here. Now when both of them, let me change the color. Okay, when both of them, A is 1, B is 1, toggle occurs. You can see here, and again and again. Okay, whenever they are, you see here they are 1 and 1, toggle occurs, change. Okay, now if I come to the next one, also the same thing. You can see here I will change the color to green. Here this is 1, and A, which is B1 and C1, all of them 1, then toggle occurred, as you can see here. Okay, now asynchronous counter, let me summarize the discussion for asynchronous counter. Each flip-flop output drives the clock input of the next flip-flop, so connect it as a clock for the next one. Flip-flop do not change state in exact synchronism with the applied clock pulses. There is delay. There is a delay, as I mentioned, in response for successive flip-flops. And the flip-flop ripple counter, due to the way of flip-flop response one after another, is a kind of rippling effect. So because it's ripple plus minus plus, or let me say 1 0 1 0 1 0, it's a ripple. For that the name came from here. Now let's come to the synchronous counter. Synchronous counter, from the name, it's working simultaneously in synchronism. Okay, now as you can see here, this is also J and K counter enable. Okay, coming here, you can see to J and K together. This is the clock for all of them coming from here. Okay, and the output is taken now to AND gate with the counter enable to be input for the next flip-flop, and going as input to the next AND with the output of the second flip-flop, which produce output which comes to the next AND with the output of the next flip-flop, and so on until we get here, and which go for the next higher steps. Okay, so synchronous working in parallel, all of the flip-flops are triggered simultaneously by clock, as we mentioned, and flip-flop change at a time, same time, because they receive the same pulse of clock at the same time. They get output through these AND gates to the output. Okay, and we need to remember that when k and j equal to 0, this maintain the value while of the flip-flop, while jk equal 1, this will be flip-flop toggles, mean changing the states. And most of the counters in a computer use this type, which is synchronous counter. We can use definitely D-type flip-flop. Okay. Now, this is another shape for the same previous discussion. Just here, we entered 1 as input here and here, as you can see. Otherwise, this is a 3 digits, okay? This is the first one, second one, no, 4, sorry, 4 digits, okay? And it's the same principle, the same working, okay? J and K equal 1, not 0. So the way of operation of the circuits, it will be counting with an increment. You see, 0, 0, 0, 0 for the first state, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, and so on. Counting, adding more, let me say, numbers to increase the counting. Now, we can make an improvement in our counter, make it what we call it up-down counter. Up-down counter, it means if it is going up, it means we started from 0, 0, 0, 0, and we finish at 1, 1, 1, 1. Okay, so an increment. Okay, while down, it means we started from the end, which is 1, 1, 1, 1, and we do decrement until we get 0, 0, 0, 0. Okay, this can be happen by using, as you can see here, up, down for this through this AND gate, and here we have inverter. Okay, so if this is 1, here will be 0, down will be closed, it will be not working. So this part, you see, will not work. Okay, will be 0 and will not work. So only 1 will go from here through this one, and this one will be work. Now let me change the color. This now this here becomes 0, the opposite, and this here become 1. So this one will not work, as you can see here, but the green one will work, which is down. Okay, so either we increase in one direction or another direction, either increment or decrement. So just put at the beginning, rather than 3 AND gates, we put in parallel another 3 AND gates and put inputs up and down. 1 for up, it means up part will work. 1 for down, it means down part will work. Now, when we want to use also the property of counter with parallel load, as you can see here, parallel load, it means we have loads inputs I0, I1 into I3. Okay, what we will do here, we will don't forget, we always try to see sum of products. So OR gate is there, OR gate here, as you can see here. Okay, but the input will be through AND. Now, load will come as input to each AND gate here, this one and the other ones, with input. Okay, now you can see also carry, because this is counting, carry if we move to higher order. Okay, so the load, if we put load here to be 1, then it means that you take these eyes. If it is 0, we cannot take it. If it is 1 here, then 0 here, then 1 here, then we can take it. If it is 0, then 0 will be here. Now cannot take it. Okay, it's work as a normal, let me say, without parallel load. And this can be discussed through this here summary truth table, or let me say state table. Clear, when it is 0, all values will be 0, clear. regardless the clock, the load, and the counter are not care, don't care. And if it is 1 clear, see the 3 cases, look to the clock. If it is positive or rising up, then we have these cases. When load is 1, input the load and don't care about the count. When load is 0, count is 1, then do counting. When both of them 0, don't change the state. Keep it as it is. And here we have binary counter with parallel load and preset. As you can see here, we added here PL, which is parallel load, which is either 1 or 0. The same previous idea for the previous one. You can see here, I call them P note, sorry, P note, P1, P0, P2, and so on. These are the parallel load. But the issue here, if PL dash, okay, is 0 here, okay, then 1 will be here, then you can load input. Okay, we make this let me say bottom to make sure either you let P input or you stop P from become input. And this is available commercially in an IC which is called 74ALS193. It is mode 16 up down counter. It's available in the internet. You can see the chip with its specification. You can purchase it also for experimental work, or to use it in one or another application. You can see here this is up counter and this is down counter to specify you are counting up or down, okay, as we explained before. And these are my input load and these are my output, okay, counting. And this is the, sorry, here the output, here the output up or down, okay, terminal down or output, and a Q represent a flip-flop output here. Now this is the opposite of the previous one. Here it's triggered at high, at low, not at high. High it means 1 and low it means 0. So this is the reset. When it is high, it means regardless what we have asynchronous reset. If it is low, no, we have different options. If PL is low, then asynchronous preset. If all of them high, it means 1 1, no change. If the down high, okay, and there is up rising up here signal, then you counting up. If the opposite, we counting down. Very easy, almost the same simple, the same principle. If I summarize this topic, we will say that binary counter can be ripple or synchronous, asynchronous and synchronous. Ripple counter use flip-flop output as input for the next flip-flop to trigger them. Synchronous counter are controlled by clock, okay, not by from the previous to the next counter, similar to asynchronous. Up-down counter can either increment or decrement stored binary count values. Counter with parallel load can be set to unknown value before counting begin. We can do it by sending signal to say 1, use the input loads, parallel loads, or 0, don't use them. Use it as a normal counter. Let me stop with this topic, and I hope you met your learning objectives for course learning objectives for this course, and see you in more courses. Thank you very much. Good luck.